Hey, what's up, everybody? Just back here in the lab, Medlock Bridge Studios, coming to you for your final lecture of the year. Our last topic, rolling motion. So, as Drake says, everybody get your roll on. So, rolling motion is the combination of both translational and rotational motion. And what happens is we're going to talk about it without slipping. And so what it means to not slip is we learned earlier that displacement is rotational displacement times radius, or velocity is angular velocity times radius, or acceleration is angular acceleration times radius. And those relationships are predicated on the fact that you cannot slip. So for every little bit of circumference that the wheel rolls, it's covering that same amount of distance. So for every full 2 pi radians that a wheel or a disc or a hoop or something will turn, that it will also roll a distance of 2 pi r radians. All right, we'll talk about a couple special cases where maybe something is slipping a little bit and then begins to roll, or what it might actually be like to slip. But you won't have to solve anything like that. You just need to understand that if you're solving for something, it's going to go without slipping. And so that means that all of those relationships where you can convert from rotational velocity to angular velocity, or rotational acceleration to angular acceleration, or rotational displacement to linear displacement, or translation as we call it, those relationships count. Those can be used, and they have to be used because your angular velocity is going to be related to your translational velocity or your linear velocity through those equations. And your angular acceleration is going to be related to your linear acceleration through those equations. Your angular displacement is going to be related to your linear displacement through those equations. Now, as I said before, every time that your wheel rolls 1 revolution, the wheel itself is covering 2 pi radians, or 2 pi r distance. That will be the linear distance. Remember from circular motion that 2 pi r divided by the period, or the time it takes to make 1 full revolution, that is going to end up being your linear velocity as well. So there's another go-between for you. One other thing to note, and we'll get into this in a few other places too, is that not slipping means that friction is in play. But it's important to remember that it is static friction that is in play, and not kinetic friction. I know you might be saying to yourself, well, yeah, but it's moving, so it's got to be kinetic friction. But the spot that is coming into contact, if you look at the blue line on the picture above here, the blue line is tracking one spot on the wheel, and that one spot on the edge, it has one spot that it's going to come into contact with the ground, and it will not slip past that spot. So it's like you walking. When you put your foot down, your foot doesn't slip unless you're walking on ice, in which case you have some form of either no friction or kinetic friction. But if your foot stays in that one spot, static friction is the thing that is at play. So to give you another way to think about it here, translational velocity means that all parts of the object are moving forward or backwards or up or down or whatever at the same speed, right? So the bottom, the middle, and the top, they're all moving linearly or horizontally, in this case, to the right. And that's if you look in one of the points here, it says that translation is relative to the background. So if you look at an object moving relative to the background behind it, all you see is it moving to the right, and all parts of it are moving at the same speed. But then if you look at an object rotating, then what you're doing is you're looking at its motion relative to its center of mass, or the place, its axis of rotation, right? And so if you look at it according to the axis of rotation, you see that the top is moving forward, but then you see that the bottom edge is moving backwards. And since rolling motion is translation plus rotation, what we see is that you add those two pieces together and you get that the top edge is moving at twice the linear velocity. The middle of the object is moving at your linear velocity, and technically the bottom edge is moving at zero velocity because it is hinging past that one spot. Because it's not slipping on the ground, it is in contact with the ground in that one spot, and that spot isn't moving horizontally at all. So its velocity is zero because the rotational velocity at the bottom has canceled out with the linear velocity at the bottom. So let's take a look at an example here about how we might think more a little bit about rolling and how things kind of work with it. And that is, let's say that we have this sphere or ring or hoop or something that is moving along at a linear velocity of v naught, but it's not on a rough surface or a surface with any friction. It's just on a smooth surface. So it gets hit with a pool cue. Let's say it's a billiard ball, right? And it gets hit and it's on ice, and so there's no friction, right? And so the moment it gets hit right in the center of mass, so there's no torque to cause it to rotate. And so since there's no friction, it won't rotate. So that means that its angular velocity is zero and its v is v naught, right? And then a little bit later, it runs into rougher ice, or let's say some patch of friction, right? And the friction is going to begin to act backwards on it. And so in phase two, the friction begins to apply a torque to the bottom edge. And so what you have is the beginning of a rotation. And so that friction isn't just doing work in terms of taking energy out. What it's doing is it's taking energy away from linear velocity. It's taking away kinetic energy that is translational kinetic energy, but it's turning some of that energy into rotational kinetic energy. So it's not just doing work in the sense of taking energy away from the ball. It's also doing work to make the ball start to spin, all right? And so some of that energy is leaving, yes, due to friction, but other bits of that energy are causing it to rotate. And so what you have in phase two is as it hits that rough patch, it doesn't just slow down, but some of that energy gets put into rotation, and so the angular velocity begins to grow, right? And then eventually when you hit phase three, where it is just in full rolling motion, or what we call no slip rolling, that's where it does have an angular velocity, and its final velocity is less than its original velocity linearly. And finally, those two velocities match up, and they match up through our v is equal to r times omega equation. And so in phase two, that doesn't apply because it still might be moving linearly faster than it is traveling angularly, meaning that if it does one full rotation, it might travel more or less than 2 pi r distance. But by the time we get to phase three, where it's rolling with no slip, then every time it does one full rotation, it's also traveling 2 pi r meters. It's also interesting to note in this situation that yes, a little bit of energy is lost while it's transitioning from going from pure translation to total rolling. So the energy can't just be divided from one to the other. And we won't do a calculation on that because that gets a little bit how much you're actually losing to friction versus how much is being pushed over into rotational kinetic energy is not something that we're gonna sit there and worry about the details of. But it is important to note that some of that is going to be lost. It's not 100% efficient as it transfers from strictly translational motion or linear motion to translational plus rotational motion, which we would call rolling motion. All right, now perhaps the hardest part about getting rotational motion into rolling motion is that you need to make sure you understand where your axis of rotation is. All right, and in order for us to work through problems that have to do with that, we have to, we have to make sure that we know about our friend Pat. Pat is how we refer to the parallel axis theorem. And the parallel axis theorem basically says, okay, I've got this object and it's rolling, which means that it's rotating on an axis that is not what we would call our derived axis, so I sub d, or our center of mass axis, which is I sub m. Those are one and the same. And so sometimes in some books you see them, or online you see them as I sub d, and sometimes you see it as I sub cm. And so basically, like let's say for example, the hoop, which is just mr squared here. If a hoop is rolling, let's say down a ramp, it's not actually technically rotating about its center of mass axis. So it's not rotating about the center. If you look just at the hoop itself and you ignore everything that's going on in the background, relative to the center, yes, it's rotating around the center. But if you pull back and you notice that it's translating, actually it rotates around the point of contact with the ground. And that's something that's kind of hard to conceive. There's a couple videos out there you can find to make sure that you see it. But it's important to note that really, in reality, when something is rolling, it rotates around the point of contact with the ground. And one thing you can do is you can get something that's round and put it on the top of your index finger. So you stick your index finger out, put that ball on the top of your index finger, and then begin to roll it around your finger, and you start to see what I mean, that the ball, it's almost like somebody hung the ball up at its radius and is just spinning around one point at its radius. And that is what's happening when something rolls, is it's actually rotating around a spot out at its radius that's in contact with the ground. That's what we call the point of contact. And so while you're looking at it, if you ignore the background, sort of like with this rod down here, the two moments of inertia for the rod, if you look at it, if you were to watch something rolling, you would think that it's rotating about the center, like the bottom derived moment of inertia for the rod, which is 1/12 ml squared. But in reality, it's actually rotating around out at its radius, much like the 1/3 ml squared one that's right above it. Right? And so what you have to do is be able to say, okay, well, I've got this thing, it has this moment of inertia, but that's for around its derived moment of inertia or its center of mass. But it's actually rotating about some other spot. And parallel axis theorem is the thing that allows you to move the moment of inertia so that it takes into account where you're actually rotating from. So in parallel axis theorem, or PAT, the moment of inertia, I pat, is equal to the derived moment of inertia plus m times d squared. And d is the distance from your center of mass, or your derived moment of inertia, to the other place that you're actually rotating from. So if you see the picture, we have some arbitrary shape, and let's say its center of mass is right there with the dashed line right through the center. But then you actually end up pinning it about a different spot that is distance d away. So then that would be I derived, or I center of mass, plus m times d squared. We'll do some examples, start to see how this kind of works. All right, now for example, we'll use the rod that I showed you before. Let's say that we know for a fact that the moment of inertia for a rod about its center is 1/12 ml squared. And that makes sense. It's pretty easy to change direction for that. Now, if I decide instead that I want to tack the rod up and let it swing from its right end, as I've noted in the right side of the picture there, I've moved the axis of rotation out there. Well, I can't say that the moment of inertia is 1/12 ml squared anymore because it's not working that way. Because it's not spinning around that middle spot. Its axis of rotation is no longer at its center of mass. And so what I need to do is use the parallel axis theorem where I say I derived plus md squared. All right, well, I derived as 1/12 ml squared. That's from its center of mass. But then I'm going to add plus md squared. And so that would be plus m times 1/2 L squared. And that 1/2 L is the distance from my center of mass, or my derived moment of inertia, out to where my new axis of rotation is. So from my old axis of rotation to my new axis of rotation is half the length of the rod. And so that's 1/2 L squared. So 1/2 L, but then I square it. All right, so then I get 1/12 ml squared plus 1/4 ml squared. I go ahead and find a common denominator, add things up, and I get 4/12 ml squared, which, when we simplify, is 1/3 ml squared. So indeed, it does actually work out, because we know that the moment of inertia for a rod at its end is 1/3 ml squared. Okay, so let's apply this to a different example where we actually have something that is being forced to move down. All right, so let's talk about a block on a ramp and a solid sphere, let's say, on a ramp. Okay, so if I put a block and a solid sphere at the top of a ramp, I put them both at the same ramp, same height up, and I let them go, who wins at the bottom? Who gets to the bottom first? Well, we can't quite compare them apples to apples like that, because the block isn't going to slide unless it's frictionless. But the ball won't roll unless it's friction filled. All right, so if we put both of them at the top of a frictionless ramp, then they're both going to reach the bottom of the ramp at the same time, going the same speed with the same acceleration, because the ball won't actually roll on a frictionless ramp, because there's no reason for it, there's no friction to apply to it to cause it to start to rotate. And so they would both just translate to the bottom. They would get to the bottom with the same speed and the same acceleration. But if we put friction on a ramp, then the ball obviously wins, because the friction actually just makes the ball roll and it reaches the bottom. But the block might not even move because there's friction there. So then what we need to do is compare them where we have a block at the top of a frictionless ramp, and we have the ball or the sphere at the top of the friction-filled ramp, right? And the question is, who gets to the bottom first and who's going faster at the bottom? And if it is a frictionless surface for the box will reach the bottom going faster. And the reason is that all of the potential energy that the box had up at the top has gone into translational kinetic energy. So mgh is equal to 1/2 mv squared. But if you look over at the sphere, it's not actually the friction that slows the ball down. The problem is the friction forces the ball with torque. It doesn't force the ball, it actually torques the ball into rotation as it begins to move down. So the ball begins to both rotate and translate. And so since the ball is moving both linearly and rotationally, mgh is now split up between 1/2 mv squared and 1/2 I omega squared. So not as much energy is going to go into the ball moving forward as it would the ball moving in, or the block moving down the ramp. So some of that energy is going to get siphoned off to help the ball rotate. So the sphere will actually reach the bottom of the ramp going more slowly, translationally, or linearly, even though both of them have the same potential, and that's because some of the energy is going to be wrapped up in the rotation of the ball. Now, back to how does this actually get solved? How do we know that? And how do I use parallel axis theorem to help me get to that problem? So we have a solid sphere of mass m. It's placed at the top of a ramp, angle theta, and released. There is going to have to be friction on the ramp. We know that already, although I'm not going to assign any particular amount of coefficient of friction or anything. You'll see why we don't really need it at this moment. And we say, okay, well, what is the velocity or the acceleration of the sphere at the bottom of the ramp? How do we solve this problem? If all you need is velocity, then you use energy. All right, now energy, you have two different approaches that you can use. If you want to use energy, then you can do it without parallel axis theorem or with parallel axis theorem. Without is on the left and with is on the right. So without, let's take a look. Without using parallel axis theorem, we say that energy initial has to be equal to energy final because, excuse me for a second, excuse me, energy has to be conserved. And so we know at the top of the ramp, mgh, that's the potential, gravitational potential that we have. But then at the bottom, some of that energy is going to be translational and some of that energy is going to be rotational. All of it kinetic, but some of it will be translational and some of it will be rotational. So what we do is we take mgh is equal to 1/2 mv squared plus 1/2 I omega squared. Now, we said that we're not going to use parallel axis theorem, so we're treating both of these as separate pieces. And what we're doing is we're handling the kinetic energy separate because we're considering the object as rolling from its center of mass. We're going to treat the translational piece separate than we will the rotational piece. All right, and so what that means is that 1/2 mv squared, there's our translational piece, and then 1/2 I omega squared, there's our rotational piece. And so we're going to let the math solve out how much of it goes into rotational and how much of it goes into translational. Now, for 1/2 I omega squared, we know that for a solid sphere, the moment of inertia I is 2/5 mr squared. And then we know, since this isn't going to be slipping, that omega is v over r. So we plug both of those in for 1/2 I omega squared, and we get everything to be in the linear language. So instead of it being in the part of it in linear and part of it in rotational, everything is now in linear language. So when I cancel my m's out, I cancel my r's out, and I end up with 1/2 v squared plus 2/10 v squared. So you can see how some of the translational energy has gone into 2/10 v squared of it has gone into rotational energy. Add those together and then solve everything out. So we get v final is the square root of 10 gh over 7. Right now, if we want to use parallel axis theorem, it's a little bit simpler because we don't have to treat rotational and translational or linear energy separately. We can say, okay, this thing is rotating, but it's not rotating about its center of mass. It's actually rotating around its point of contact with the ground. And so since it's rotating around its point of contact with the ground, we're also taking into account its linear motion, right? So that means we need to use parallel axis theorem. Well, parallel axis theorem is I center of mass plus m times d squared. So that's 2/5 mr squared plus mr squared. And it's r squared because the axis of rotation has moved out to the edge of the radius. And so that's r distance away. So we plug in mr squared and we get 7/5 mr squared is our new IPAT or moment of inertia using parallel axis theorem. So we plug that in. And because we're rotating around that new axis of rotation, we're also taking into account the linear pieces. And mgh is equal to 1/2 of 7/5 mr squared times omega squared, which again, we're in a no slip situation. So v squared over r squared can get plugged in there. So then gh is equal to 7/10 v squared, and we solve for v final, and would you look at that, it's the square root of 10 gh over 7. All right, let's remember that, shall we? Okay, let's remember that this takes a lot of work and a lot of practice. So if you need to look up more videos, you need to ask me questions, You need to make sure that, whatever you need to do, make sure you get that work done, because this is something that takes some practice. You can't just walk in and do it for the first or the second time in an exam. All right, and you want to be ready for that when you do the AP exam. All right, so maybe we don't just want velocity. Maybe we need acceleration, or maybe that's all we need is acceleration. In which case, we're going to have to take a different approach, because energy is very good at getting you a final velocity. Energy is not very good at telling you what acceleration or time would be. All right, and maybe we need those pieces. In which case, we have two approaches. We can use PAT or we can not use PAT. So in approach 1 here, we're going to ignore parallel axis theorem. And we're just going to try to find the acceleration and the final velocity using torque and kinematics. And when we do that, that means we have to draw a free body diagram. And so remember, when you have a free body diagram, especially of rotating objects, you draw the forces where they act from. So normal acts from contact, point of contact with the surface, weight acts from the center of mass, and friction is going to act from the point of contact between the ramp and the object that is rolling. All right, so I take my object here, I drew my free body diagram, and I go and I sum the torques, and I know that the sum of the torques is equal to I times alpha. So again, before I get into this, I just want to remind us that this is approach number 1 of the 2 different ways that we can do this, and that is that the axis of rotation is going to be around the center of mass for this. So if it's around the center of mass, that means the moment of inertia is going to be whatever the derived moment of inertia is for a solid sphere about its center of mass. And that means we're not going to use parallel axis theorem. All right, so if I sum the torques, then I'm assuming that this thing is just rotating, and that means that I sum the torques around the axis of rotation. When I do that, you see that friction is the thing that causes the rotation, and that the weight and the normal force both move through the axis of rotation. And since they both move through the axis of rotation, their radius is 0, which means even though they're forces and they're actually there and acting, they cause no torque. So in some of the torques, it's just friction. Friction times radius is equal to I alpha, or friction times radius is equal to 2/5 mr squared times alpha. This is a no-slip situation, so alpha is equal to A over R. So I get friction times radius, that's the only torque I have, which is equal to 2/5 mr squared times A over R. And I know some of you might think, well, how do we know that it's accelerating? Maybe because there's friction there, it's slowing it down. But you only have one object causing a torque on something. Remember when we had forces, we said that if there's only one force, one net outside force acting on an object, it has to be accelerating. It could be slowing down, it could be speeding up, but it has to be accelerating, right? And the same thing with torque. If there is only one torque acting on an object, it has to be accelerating. All right, so we get this F times R, or friction times radius, is equal to 2/5 mr squared times A over R. Now, I don't have anything for friction. I wasn't given a mu, so what we need to do is we need to go back and we need to sum the forces. So we go back and we sum the forces in the x direction, because I'm not going to do it in the y direction, because I know in the y direction, because this is a ramp, when I sum the forces, I rotate the ramp until it's horizontal, and that means I have to break my weight into x and y vectors. So my x vector is mg sine of theta, and my y vector is mg cosine of theta. But I know that normal and mg cosine of theta just offset each other. There's no acceleration in that direction. They're just static. So I'm not going to give a sum of the forces in the y. But sum of the forces in the x, mg sine of theta, minus the friction, is equal to ma. And this is a place where students, if they haven't practiced enough, they start to get confused. Because when you're talking about rotation, you say, oh, well, things are going through the axis of rotation, or things are not. And So when we look at torque, we know that normal and weight are going through the axis of rotation, so they don't count for torque. But when we're looking at translation, we don't care where the force acts from, we just care in what direction it acts in. So if it's in the x direction, we count it. And so kids get caught between those two rules because they haven't practiced enough. So make sure you practice this enough to where you understand that when you sum the forces, it doesn't matter what the axis of rotation is, because there is no axis of rotation. So mg sine of theta minus friction is equal to m times a. So I resolve for friction, and I get mg sine of theta minus ma. I take that and I plug it back in for friction in my sum of the torques equation. And as I boil it down, I find that acceleration is 5g sine of theta over 7. Now, if I want to know, that's the acceleration going down, right? So that's not just g sine of theta, that's 5/7 g sine of theta. So yeah, I've lost a little bit of acceleration because some of that energy is being put into making the object rotate. Now, let's say I want to find the velocity using kinematics. Well, it's on a ramp, and so I know the height of the ramp is h, and I know that the angle is theta. So I use sine of theta is h over delta x, which is the distance, because remember, linearly we've rotated that ramp, and delta x is the hypotenuse. That's the distance that we're actually traveling down. And then I get that delta x is h over sine of theta. And then I come back to my kinematic equation, vf squared is equal to vi squared plus 2a delta x. And I start plugging things in. I know that v initial is 0 because I release it from rest. And then I know that acceleration is 5/7 g sine theta. And I know that the distance x is h over sine theta. And I cancel stuff out, and then I bring my square root over so I can get v final is, would you look at that, square root of 10gh over 7, or 10/7 gh. Where have we seen this before? Yeah, that's deep. All right, in approach 2, we're going to use parallel axis theorem because we're going to assume that the axis of rotation is actually at the point of contact between the sphere and the ramp. So we got to call our friend Pat, right? And so approach 2, we're going to have the same free body diagram, except we're assuming our axis of rotation is at the point of contact. And then what we figure out is that torque is caused by the weight, which is a small distance over the axis of rotation, right? But then we also notice that normal and friction are through the axis of rotation, so they cause no torque. So I write my sum of the torques, and I get mg sine of theta times r is equal to I pat times alpha. All right, so we need our parallel axis theorem. So I go through, and I know that we did this with the energy problem earlier, but we know that it's I derived plus md squared. And so that is 2/5 mr squared plus, and then it's radius r away at the edge of the sphere, so that's mr squared. And that ends up being 7/5 mr squared again. So I plug it back in, and I get mg sine theta times r is equal to 7/5 mr squared times alpha, and we know that this is a no-slip situation. So the linear to angular equations count, and so that's a over r. And would you look at that, 5/7 g sine theta is our acceleration. Okay, so I take back, I go back to my same kinematic equation. I want to know what is the velocity at the bottom doing this, and I get vf squared is, plug everything back in. Oh, I need a distance. Well, I know that I'm coming down this ramp. This ramp has a length of delta x. I know that sine theta is h over delta x, and blah, blah, blah. Plug that back in, and v final is equal to the square root of 10/7 gh. In the words of Keanu Reeves, whoa. Okay, so just a reminder that if you are in a no-slip situation, right, then the rules that we've talked about, where you can count on for every single full rotation not only are you rotating 2 pi radians, but you're also traveling 2 pi r meters, right? Then the acceleration linearly is equal to alpha times r, and the velocity linearly is omega times r. Okay, so that is it for this, your final lecture. And I just want to remind you again that this will take some practice. It is something that can be confusing. So the most important thing to remember is understand the conceptual stuff that's happening first. Understand that some of the energy is being transferred into making something rotate so it won't travel as fast. Understand that if you are rolling and you're not slipping, then every time you turn 2 pi radians, you're also traveling 2 pi r meters. Make sure that you are cognizant of the fact that if you're rolling and not slipping, that means that your velocity at the bottom is technically 0. Your linear velocity is, because you are under static friction, and that spot is not slipping at all. Meanwhile, up at the very top, technically, because you're rotating around an axis that is not at its center of mass, but down at its point of contact, that means that you're actually traveling much faster up at the very top edge, because it is rotating around the spot at the very bottom. Okay, so I'm sure there's going to be lots of questions about this. I'm sure that we'll need to make sure that we have a couple of help sessions for this. Just reach out, make sure you get stuff on Teams. And, you know, since this is our last lecture, I do want to say I really appreciate how much work you guys have done this year. I think you guys have come a whole long way. I know this is not the way that we would want to ever end our last lecture, but I do want to say congratulations for making it to the end. I'm proud of all you guys. And I hope that you just keep staying away from each other. And I hope that you guys are doing well. But for now, just remember to stay classy. That's it from Medlock Bridge Studios. That's it from the lab. See you guys